New Deep Dive.
Welcome to the deep dive. Ever wondered what kind of wild, spectacular things might be happening way, way above your head? Stuff you never even knew about. Today, we're giving you, well, kind of the ultimate shortcut to understanding a phenomenon that's so incredible it feels like it just jumped straight out of a sci-fi movie. Our deep dive today is all about atmospheric specters, sprites, and luminous events from space. And we've pulled together some really intriguing sources for this. Everything from these rare, frankly breathtaking astronaut
Oh
photos
yeah, some of those are
near
open
the
loop.
real cutting edge science that breaks down the chemistry, what's actually going on. So, our mission to unpack these really mysterious high altitude light shows, figure out the chemistry, and look at how we're finally getting a clear view of them. And what better way to kick things off than with something pretty recent and just jaw dropping? Just a little while back, NASA astronaut Nicole Ayers, she captured this stunning photo of a rare red sprite from the International Space Station.
That was a fantastic capture.
Right, she was flying over Mexico and the southern U.S., and this wasn't just, a cool picture for her feed. It actually provided really valuable data for scientists who study these fleeting atmospheric wonders. It gives us a window into a world we barely knew existed. That photo from Nicole Ayers is just incredible, but it makes me wonder, what exactly are we looking at there? I mean, is it just fancy lightning or is it something else entirely? What are these transient luminous events, or TLEs anyway?
That's a really good question. And the key thing, I think, is that TLEs are essentially these short-lived optical events. Light shows, basically. They happen way up high in the atmosphere, specifically above the really intense thunderstorms.
Above them, not within them.
Exactly, much higher up than regular lightning, which is down in the clouds.
Mhm.
And TLEs, they take on all these different fascinating forms, really distinct looks. And these events are incredibly brief, like typically lasting from less than a millisecond
Wow.
to maybe just over 2 seconds at the absolute longest. They're a big, though often unseen part of Earth's global electrical circuit. What's interesting is pilots had reported seeing things like this for years, anecdotes mostly.
Right, I've heard those stories.
But it wasn't until 1989 that they were actually first properly documented with photos, officially confirmed. And that kind of explains why they're so rarely seen with the naked eye. They're short duration, plus they're relatively faint. You really need sensitive cameras to pick them up, which is exactly why astronaut observations like that photo are so groundbreaking.
It's like trying to photograph a ghost, basically. High up and super fast.
That's a pretty good analogy, actually. A ghost 100 kilometers up, flashing
Yeah.
for a fraction of a second.
Okay, so when you say distinct phenomena, how distinct are we talking? Are they just like variations on lightning, or are we finding a whole new family of atmospheric light shows?
Oh, we're absolutely talking about a whole family. It really shows how complex atmospheric electricity is, much more than we thought. The main types of TLEs are incredibly diverse. So first, you've got sprites.
Sprites, okay.
Those are the red flashes, often looking like giant jellyfish or maybe carrots reaching up to 100 kilometers above the clouds. That's what astronaut Nicole Ayers photographed recently.
The jellyfish ones, right. I think I've seen illustrations.
Exactly. Then there are blue jets. These are different. They're narrow, sort of conical discharges that shoot upwards from the very tops of storm clouds.
Blue jets shooting up.
Yep. And then you've got elves. ELVES.
Resolves, like the mythical creatures.
Sort of. It's an acronym, actually, but the name stuck. These are rapidly expanding luminous disks. Think of a ripple spreading out incredibly fast. They can grow huge, maybe 500 kilometers across.
Whoa.
But they last for less than a millisecond, just unbelievably fast,
Gone in an instant.
pretty much.
Yeah.
And then the newest members of the family, ghosts,
Ghosts. Okay, now it really sounds like sci-fi.
doesn't it? These are greenish flashes that pop up above intense elves. And what makes ghosts really unique and honestly exciting for scientists is that they seem to be formed mainly by iron and nickel compounds.
Iron and nickel, not oxygen or nitrogen like the others.
Exactly, which is totally different. It's huge because it hints that these metals are present high in our atmosphere, maybe from, meteoroids burning up. Stuff like that, unexpected chemistry.
It really sounds like these TLEs are way more than just a pretty fleeting light show then. Does this mean lightning itself has a deeper impact? That'd be an unseen influence on our atmosphere that we're only just starting to get a handle on.
Absolutely, yes. Beyond the visual spectacle, lightning plays this crucial and maybe surprising role in atmospheric chemistry, especially way up high in the
Yeah.
mesosphere. You need to think about lightning not just as this powerful flash and bang,
Right.
but almost like a hidden chemical factory up in the sky. It's constantly sort of fertilizing our planet and cleaning the air in ways we don't often consider. So there's this process called nitrogen fixation. The intense heat and pressure from a lightning discharge literally breaks apart the stable nitrogen gas in the air.
Which is most of the air, right?
That's the one. NERO. Very stable. But lightning converts it into reactive nitrogen oxides, things like nitric oxide, NO, and nitrogen dioxide, NO. And the scale is pretty significant. Estimates suggest lightning produces maybe up to 14.4 million tons of these nitrogen oxides every year.
Wow, 14.4 million tons. That sounds like a massive amount. How does that stack up against, say, human sources or other natural processes? Does it really shift the needle in our atmospheric models?
It's definitely a major natural input. In some regions or contexts, it can be comparable to certain industrial sources, believe it or not. And these lightning-produced nitrogen compounds, they don't just vanish. They can react further, like with water in the atmosphere, to form nitric acid. Okay. And eventually, that nitric acid reaches the ground as nitrate in rain or snow. It's basically a huge part of the global nitrogen cycle, a natural fertilizer delivery system for ecosystems.
A fertilizer from lightning? That's amazing.
It really is. And higher up in the upper troposphere, these compounds actually increase the concentration of nitrate aerosols' tiny particles by over 50%. This directly impacts the atmosphere's oxidizing capacity, its ability to cleanse itself of pollutants, and it changes how these tiny aerosol particles behave. And another crucial point, these particles actually make the air absorb more water at a given humidity level.
Okay, so they make the air slightly moister.
In a way, yes. Or rather, they change how the existing moisture interacts with the aerosols. This alters how these particles reflect or absorb sunlight, their radiative properties, and that could potentially influence how clouds form.
So influencing weather and climate, potentially?
Potentially, yes. It's an active area of research, and there's another critical chemical process, too.
More chemistry.
More chemistry. Lightning also creates ozone. Oh. This happens when the UV light from the discharge breaks down those nitrogen dioxide molecules we mentioned, releasing single oxygen atoms, which then quickly combine with regular oxygen molecules, OO, to form ozone.
So lightning makes ozone, too. I thought ozone was made differently.
It is made in other ways, too, like by sunlight higher up in the stratosphere, but this is a significant source lower down. It's basically a natural mechanism for cleaning the lower atmosphere, scrubbing pollutants. It complements that nutrient delivery system we talked about. So yeah, next time there's a huge thunderstorm, don't just think about getting wet.
Right. Think about the planet's hidden fertilizing and cleaning system going full blast overhead.
Exactly.
Okay, this is all fascinating, but given how fleeting and faint you said these things are, how on Earth, or maybe off Earth, do we even manage to see them properly? What gives us this unique viewpoint you mentioned?
That's the key challenge, isn't it? And turns out the International Space Station, the ISS, is just an unparalleled platform for this kind of observation. Watching storms and all this atmospheric electrical stuff from space. Its position, its orbit is just strategically perfect. See, the ISS orbits about 400 kilometers up. That's roughly 250 miles. And its path, its orbital inclination.
The angle it orbits at.
Right, it's tilted at 51.6 degrees. This means it covers almost all the low and mid-latitude areas of Earth where most intense storms happen. And it sees them at all different times of day and night. This brings its instruments incredibly close to the action, much closer than any other satellite platform, giving us that unique perspective you just can't get from the ground. And they use several really specialized observation techniques up there. For instance, they often use an oblique viewing angle, looking sideways or down at an angle.
Not straight down.
Not always. This oblique view lets them figure out the exact height of the electrical activity, like the sprites or jets, and also see the cloud structure in detail. This gives us crucial data on how these storms are impacting the atmosphere's energy balance, the radiative properties, and ultimately, the climate.
Got it. So the angle helps measure height and structure.
Precisely. Then you have the specialized instruments themselves, like the Lightning Imaging Sensor, LIS, which has been up there, and the Atmosphere Space Interactions Monitor, ISIM. That's a big European Space Agency instrument.
LIS and SM. Okay.
These are specifically designed to record not just regular lightning, but also the TLEs, the Sprites, blue jets, elves, all of them, which are, as we said, incredibly hard to spot from Earth's surface. The ISS also uses really advanced cameras, multispectral cameras. They can see light across different wavelengths simultaneously.
Like UV, visible light, different colors.
Exactly. Ultraviolet, blue, red light. They have photometers measuring brightness very precisely at these wavelengths and cameras that can snap pictures incredibly fast, maybe 12 frames per second. And the resolution is pretty good too, down to about 400 meters per pixel from orbit, so they can see details within these events.
Seeing what our eyes just can't.
Absolutely. And the tech keeps getting better. Now they're even using AI-assisted systems. You have these high-resolution cameras with very sensitive low-light sensors, even infrared sensors. And AI helps them prioritize. It tells the cameras, okay, there's a big storm system developing here, point the instruments this way, maximizing the chances of catching these faint, fleeting TLEs with much greater clarity.
So it's like having a really smart eagle-eyed spotter in orbit, always watching, ready to capture the magic.
That's a great way to put it. Always watching for those flashes in the upper atmosphere.
Wow. What an incredible deep dive this has turned out to be. We started off with that amazing photo of a red sprite from the ISS, and along the way we've uncovered just so many aha moments, haven't we?
It's a fascinating field.
I mean, who knew there was such an incredible diversity of these transient luminous events? From those majestic sort of jellyfish-like sprites to the super fast elves, and even those newly found metallically tinged greenish ghosts. And we explored the hidden chemical power of lightning. It's not just a spectacular flash that makes you jump, is it?
Not at all.
It's the silent force doing nitrogen fixation, creating ozone, profoundly shaping our atmosphere, and incredibly even fertilizing the planet.
A fundamental process.
And finally, seeing the absolutely critical role of the International Space Station. It provides that perfect vantage point, the cutting-edge tech needed to actually unveil these mysterious phenomena that, were once just stories pilots told. It really makes you wonder, doesn't it? What else might be happening up there completely unseen? Things we're only just beginning to glimpse with all this new technology and these new perspectives from space, and maybe how understanding these fleeting, ghostly events could actually help us better grasp Earth's interconnected systems, our atmosphere, our climate, the whole picture. Definitely something to ponder until our next deep dive.
Subscribe. New Deep Dive.